Hi, I'm sorry I couldn't be there today. I'm hoping that this recorded lecture will help you better than if I was there because you can rewind, fast forward, do whatever you need to do with this lecture, take notes however you want. But I'm going to be using this lecture platform here to introduce you to your next unit, Unit 4. And I'm going to record this lecture in the same order in which your slides are presented. So make sure you log on to Schoology and download those slides. If you can have them side by side with you through the course of this lecture, it will be useful. I won't pull up the slides here on screen because I want you to have that by the side. I'm just going to treat this screen right here as my whiteboard like I would if I were in class, and teach you the concepts that you need to know from your slides. So Unit 4 is all about chemical bonding. So if you think about what chemical bonding means, we've not really talked about atoms coming together. We've talked about atoms by themselves, and that's kind of the whole point of, say, for example, radioactivity. We talk about uranium, it decays to thorium and an alpha particle, but we're just talking about uranium, we're just talking about thorium, or we're just talking about an alpha particle. We don't talk about the possibility of there being any kind of binding or bonding. And even in the previous unit, when we were talking about periodicity, we were talking about, hey, what's the reactivity of calcium compared to magnesium? Or what's the reactivity of magnesium compared to aluminum? We weren't really talking about how do different elements get together to form compounds. So for example, one of the compounds that keeps you alive, H2O, water. What brings two hydrogens and one oxygen together and holds them together long enough for you to be able to use it and be alive with, which is pretty much all the time, right? At room temperature, you need liquid water. So this chapter is dedicated to learning about how different elements bond, what are the types of bonding, which one is stronger, which one is weaker, what's the consequence of all of that. And we're going to eventually use this to talk about basically how different materials work. So in chemical bonding, there are three types of bonds. There are the covalent bonds, there are ionic bonds, and then there are metallic bonds. Now, I'm not going to spend too much time talking about metallic bonds because we covered most of metallic bonds in Unit 3. When we talked about the sea of electrons, how they spread out, why do these sea of electrons give metals their different properties. So I'm not going to cover this in this lecture. If you need more resources on metallic bonding, please go ahead on YouTube and search for metallic bonding. There are a lot of good videos uploaded on the topic. What I am going to cover today are covalent bonds and ionic bonds. And we're going to start with covalent bonds here. So covalent bonds are different from ionic bonds because in covalent bonds, electrons are shared, whereas in ionic bonds, electrons are transferred. This is the most simplistic way to look at the difference between these two bondings. Of course, there's more to it than just that, and that's kind of what we're going to learn about here for the rest of the lecture. So let's start with covalent bonds. So the way covalent bonds work, and to explain covalent bonding, I'm going to use the simplest element available to me, which is hydrogen. Hydrogen is basically one proton and one electron around it. Now, if you think about hydrogen with just one electron, its nearest noble gas is helium. And on the side here, let's think about what helium looks like. Helium is basically, you've got your nucleus and you've got two electrons around you. And in the previous unit, we learned that helium is a noble gas, and most noble gases tend not to react with anything, which means we consider noble gases to be stable. And we consider their electron configuration to be stable. So now if I look at hydrogen over here in blue, I know that hydrogen has only one electron, and if it could get one more electron, it could have a stable configuration like helium. So let's think about how can this hydrogen get another electron? Let's say there's not a metal around in the vicinity for it to steal an electron from. So let's say instead there's just one more hydrogen in the vicinity who is also looking for an extra electron. How can these two hydrogens come together and solve their problem? Well, that's covalent bonding. So what happens in covalent bonding is that two atoms get together and they decide that they're going to share a certain number of valence electrons. Usually the number of valence electrons from each for the sharing is equal. So if the hydrogen on the left brings 1 electron, the hydrogen on the right also brings 1 electron. And what ends up holding this entire structure together is the fact that these electrons right here, which we know are shared electrons, are being attracted by both nuclei simultaneously. So what keeps a covalent bond together is the attraction between the two nuclei. Well, not to each other. We know that the two nuclei are not going to attract each other because they're positively charged, but it's between the nuclei and the shared electrons. So covalent bond stays together because of this attraction between the shared electrons and the nuclei. But there's one more thing about covalent bonding you need to know, which is that you would think that because of this attraction, these two atoms could get really super close to each other. That can't be the case either because there's a sense of repulsion as well. So there's a repulsion between the two nuclei. So we know both of these nuclei here are positively charged and they repel each other. So there is a sense of repulsion because there are two nuclei with positive charges. So if you look at your slides that is showing you all of these different attractions and repulsions, covalent bonding is basically a delicate dance between this attraction between the nuclei and the shared electrons and this repulsion between the two nuclei and the repulsion between these electrons. So there are three different forces in play. At the end of the day, covalent bond sticks together because this wins out. Your attraction between the nuclei and the shared electrons wins out. But the repulsion between the nuclei and the electrons ends up determining how far two things are from each other. And that's more about bond length, and we'll get to that here in a second. I want you to understand a couple more things about covalent bonding before we can start talking about bond length. Now, you learned in the previous unit about electronegativity. Electronegativity is going to play a very central role in this particular unit. So last unit, I emphasized that whenever you talk about electronegativity, we're talking about the ability to attract shared pair of electrons. So what we mean by that is if I have, say for example, let's go back to our two hydrogens because they're the simplest ones to draw. And just to be clear, I'm going to use different colors to show the two different hydrogens. So I'm drawing one in red, drawing one in black. So electronegativity is basically the tendency of each of these hydrogens to pull these shared electrons towards each other. Now here's the thing, they're both hydrogen. Both of these are the exact same element, which means that both of them are going to have the same electronegativity. And what it means to have the same electronegativity is, yeah, they're both pulling on the shared electrons, but since they're both pulling with the same electronegativity, think of this as a tug of war between two people that are equally strong. So let's say I have these two people who are equally strong and it's a tug of war. Well, they're not going anywhere, right? They're each going to be pulling with the same amount of strength. That rope is going to stay dead center. Same way, these electrons aren't really going to move towards one hydrogen over another. Like they're going to be shared exactly in the center of these two hydrogens. Let's take another example. Let's take fluorine as an example. So if I consider fluorine, I'm not going to draw all 9 protons, obviously. Let me just quickly do a sketch of the electrons here. We know that fluorine has 7 electrons. So 1, 2, 3, 4, 5, 6, 7. And then let me draw the other fluorine in red here, drawing it from the outside to the in. Notice how we're sharing we're sharing 1 electron each. So 1, 2, 3, 4, 5, 6, 7, and those are my two 1s electrons. So in fluorine, since both of these are again the exact same element, they are going to pull these electrons the exact same amount to each other, because both of these again have the same electronegativity. So we're talking about a tug of war here that nobody's going to win because both sides are equally matched. So whenever you have a covalent bond like this, where the shared electrons are being equally shared, we call this a non-polar covalent bond. So a non-polar covalent bond pulls the electrons equally on both sides. So clearly not all the elements are going to bond to themselves over and over again. If that happened, there wouldn't be much of a variety, right? Then how do you explain things like H2O? I mean, clearly H2O has two hydrogens, yes, fine, but it's also got this one oxygen, and oxygen most definitely has a different electronegativity compared to hydrogen, because we know that as we go across the period on the periodic table, the elements get more electronegative, which means oxygen is more electronegative. So now let's talk about what does it mean for a covalent bond when I don't have two of the same elements. I instead have one of them be a different element. So let me take fluorine again as an example, just because we've been using it so far. So here are my two 1s2 electrons. 1, 2, 3, 4, 5, 6, 7. Now let's say fluorine is not sharing electrons with another fluorine. Let's say instead it's sharing its electrons with hydrogen. Hydrogen has only one electron, and so hydrogen is sharing one electron with fluorine. So since these are shared electrons, you can double count them for both atoms. Like for hydrogen, for example, it counts 2 electrons for itself, because the red electron from fluorine is technically being shared with the hydrogen. So now hydrogen has the helium electron configuration. And by that same token, you can look at fluorine and say, hey, fluorine is sharing the blue electron from hydrogen. So you have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So each of them has the noble gas structure. Each of them is more stable because of this bond. So we know this covalent bond works to get both of them the stability they require. But we also know that the two of them are of different electronegativity. So what does that mean for this particular bond, that they're of different electronegativities? What that means is, let's say I draw this a little more simplified. So let's say I'm just going to write H for hydrogen instead of drawing the rings every single time. And I'm going to represent its electron with a blue dot. And I'm just going to write F for fluorine. And because we know that these two electrons don't really participate in anything, I'm just going to draw these 7 electrons on the outside, because we know they're the ones that are doing all the magic with chemical reactions. So we know that fluorine is going to contribute 1 electron to this covalent bond, and the rest of them are going to be around. So what does it mean that there's a difference in electronegativity? Well, that means one of these atoms is going to pull the shared pair of electrons closer towards itself. Now we have to figure out which one is going to do that. So when I look at my periodic trends, I know that fluorine has a higher electronegativity. So because fluorine has a higher electronegativity, it has a greater tendency to pull these electrons towards itself. And since hydrogen has a lower electronegativity, it's just going to let fluorine do that. So this particular bond here is called a polar bond. It's still a covalent bond because the electrons are still being shared, but it's called polar because now there are 2 poles to this situation. So if I simply write out hydrogen fluoride, so instead of this complicated drawing over here, let's simplify it a little further. And we just write out hydrogen fluoride, like so. what that means, the single line in the middle is representing the bond. What a polar covalent bond means is since these pair of electrons are basically closer to fluorine than they are to hydrogen, it gives fluorine an overall partial negative charge. Notice how I'm not saying it's a -1 charge. I am not quantifying the amount of negativity fluorine has. I'm saying it is a partial negative charge, and I'm showing the partiality with the lowercase Greek letter delta, and hydrogen has a partial positive charge. So what that means is now we have two poles, kind of like the Earth has two poles. You have a North Pole and a South Pole. Batteries have two poles. They have a positive pole and a negative pole. Hydrogen fluoride has two poles. It's got a partial negative pole, as recognized by the fluorine, and a partial positive pole, as recognized by the hydrogen. So think of this as a tug of war, except now instead of being between two equally matched opponents, one of the opponents is definitely bigger and stronger. So if these two were going to play tug of war, obviously whatever they're tugging is going to get closer to the bigger and stronger person. So instead of thinking about this in terms of bigger and stronger, think about this in terms of being more electronegative. So since fluorine is more electronegative, it pulls the electrons closer towards itself. And because of this, we form a polar covalent bond, and we say that polar covalent bonds are dipoles. So think about what the word dipole means. The word di means two. The word pole means there's, well, two opposite poles. We know that there's a positive and a negative. So dipole means you've got two poles. One of them is positive, one of them is negative. Now, not all polar covalent bonds are the same. If you are looking at your polar bonds, some bonds are actually more polar than the others. So how can you tell the polarity between the two bonds? Take whatever two elements you're studying. So let's take a few examples. Let's take HF, HCl, and HBr. Notice how for all of these, one thing is the same. It's hydrogen bonding to one of the halogens. Now, if you think about fluorine, chlorine, and bromine, out of the three of these, fluorine is most electronegative, and bromine is the least electronegative, which means out of these three bonds, since hydrogen was the same every single time, it was the same electronegativity, and the only thing we were changing is fluorine, chlorine, or bromine, out of all of these three bonds, the hydrogen-fluorine bond is the most polar bond. And out of these three bonds, this is the least polar bond because the difference in electronegativity. So we're looking at the difference in electronegativity, which means if you took the actual electronegativity value of hydrogen and you subtracted the electronegativity value of bromine and compared whatever number you got to subtracting fluorine and hydrogen's electronegativity values, there would be a difference between them. And I've shown you this difference on slide 7 in your slide deck, where I'm showing you polar covalent bonds, and you look at HF, HCl, HBr, HI, and we find that the difference in electronegativity gets smaller and smaller and smaller, which means that they're not a dipole, like they're not as strong as a dipole as you go down the group because the electronegativity is decreasing. So I want you to try the pair and share question before you skip over to the answer. It's arranged so that you have to click twice to get to the answer. So try doing those two sets on your own to see if you understand how you can arrange bonds in terms of increasing or decreasing strengths based on their electronegativities. Pause the video while you do that, and then you can move on to the next part of this video. All right, so now that you know what bond polarity is in covalent bonds, there are two more things that I want to talk to you about. I want to talk to you about covalent bond strength and covalent bond length. So we're going to look at both how strong these bonds are and how long these bonds tend to be. So let's talk about bond strength first. We measure bond strength in terms of bond enthalpy. This might be the first time you're encountering this word. I promise you it will not be the last time. We're going to focus on enthalpy a whole lot more in second semester. But for this semester, what I need you to know about the word bond enthalpy is it's simply the energy needed to break a bond. I mean, it's a little more complicated than that, but for now, just know that it's the energy needed to break a bond. And by this statement, now you have another new piece of information. You know that energy is needed to break a bond, which means if you want to break a bond, you have to physically add more energy to do that. And let's talk about why that is. So we discussed what holds bonds together. So if you take two hydrogen atoms, for example, that have a single bond, we said you have your nucleus in the center for both of them, and then we're sharing electrons. So let's say we're sharing this blue electron and we're sharing this red electron. We said that there's an attraction between the nucleus and the shared electron, the nucleus and the shared electron. So we said there's this attraction going on. If you want to break this bond, you are going to have to cut through this sense of attraction, right? You're going to have to break the attraction that the nucleus has to the shared pair of electrons. And to break an attraction and to move an electron further away from the nucleus, you need to supply it with energy. So covalent bond strength is basically the more energy you provide, the more likely you are to break a bond. So let's talk about what exactly determines what can break a bond and how much energy you need. So I'm going to take three examples here. I'm going to take fluorine, oxygen, and nitrogen. So take a second to locate fluorine, oxygen, and nitrogen on your periodic tables and notice how they're right next to each other. So they've got some pretty similar electronegativities. They're some of the most electronegative elements in your entire periodic table, and they engage in covalent bonding. So with fluorine, let's say I have two fluorine atoms. Let's say I have two oxygen atoms and two nitrogen atoms. And let's draw their electrons in. So let's say I'm only drawing the valence electrons. Mind you, I'm not drawing the 1s2 electrons because they're not really going to play a role in bonding, as we know. So fluorine has 7 valence electrons, oxygen has 6 valence electrons, nitrogen has only 5 valence electrons. You'll notice that I've drawn them a little differently for both, and that's very deliberate because I'm trying to show you the difference between a single, double, and triple bond. So whenever covalent bonds form, they form in order to get octets, right? So if I look at fluorine, for example, consider the middle 2 electrons to be shared, no matter how you count this. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 electrons for each fluorine. Same way for oxygen, 1, 2, 3, 4, 5, 6, 7, 8. By sharing 2 electrons each, oxygen is getting its octet. And by sharing 1, 2, 3, 4, 5, 6, 7, 8. By sharing 3 pairs of electrons, nitrogen is getting its octet. So what's going on here is fluorine has a single bond because it's sharing only 1 pair of electrons. Oxygen has a double bond because it's sharing 2 pairs of electrons. And nitrogen has a triple bond because it's sharing 3 pairs of electrons. Now let's talk about the difference between these. We know that in the center, I'm going to remove the symbols here since we know which elements we're talking about. Oops, forgive me about that. Since we know which elements we're talking about, I'm going to remove their symbols. That way we can draw a nucleus in the center and talk about bond length and bond strength from the perspective of the nucleus. So instead of writing the symbol, I'm going to put positive charge in the center since we know there's a nucleus there. And we'll pretend these represent the nuclei of fluorine, oxygen, and nitrogen respectively. So we know that in fluorine, the 2 electrons are being attracted to each nucleus. So in fluorine, we have 2 shared electrons attracted to the nucleus, or to each nuclei, really, it's to both nuclei. Here we have 4 shared electrons attracted to each nuclei, and here we have 6 shared electrons being attracted to the nuclei. I want you to remember the activity we did last unit on Coulombic forces of attraction. If you don't remember it, the Unit 3 folder is still on Schoology, and that Coulombic forces of attraction activity is still there. I highly encourage you go take a look at it because Coulombic forces are a big deal in bonding. But what our Coulombic forces basically said is the more charges you have, so having 6 electrons instead of 4 or 2, the more charges you have, the more the attraction is. So you have the strongest attraction on the triple bond because there are 6 shared electrons being attracted to each nucleus. So because our triple bond has the strongest attraction, the triple bond is the strongest bond, which means it has the highest bond enthalpy. It's the strongest bond, basically. And since only 2 electrons are being shared in a single bond, this one is a low bond enthalpy. And then the double bond is somewhere in the middle of these two. So the moral of the story here is that a single bond is weaker. And that if you compare that to a double bond is stronger because you have 4 electrons being attracted to the nuclei, and that a triple bond is going to be the strongest of the three. Now let's talk about what does that mean for bond length. So if we're looking at bond length, and I'm just going to take one of the examples here. So if you take nitrogen, for example, you have 3 electrons from each being shared. Now, the nuclei are pulling at these electrons. It's going to be a stronger pull. We know from the previous unit that when the nucleus has a strong pull on its electrons, the atom gets smaller. So here, same logic. The nucleus has a strong pull on these electrons, so the bond gets closer. So triple bond is not only the strongest, it is also the shortest. And single bonds are not only weaker, they are long bonds. And double bonds are somewhere in the middle of single and double bonds. So if you go to the slide that says bond enthalpy and bond length, I've given you some numbers there to show you what that means. So you see that they're in that particular slide, you'll see that we're comparing carbon single bond carbon, carbon double bond carbon, carbon triple bond carbon. And it looks like the bond length for a carbon single bond carbon is 1.4 angstrom. Angstrom is just 10 to the power negative 10 meters. It's a way of measuring length. Double bond is 1.34 angstrom. And this triple bond is 1.20 angstrom. So notice how the triple bond is the shortest. Now, if we were to actually look at bond energies for these carbon bonds, carbon single bond actually has a bond enthalpy of 614 kilojoules per mole, whereas carbon double bond has a bond enthalpy of 839 kilojoules per mole. So we can see that the double bond is stronger than the single bond because it takes more energy to break. So what I'm going to do is I'm going to stop this video here so that this video is just about covalent bonds, and then I'm going to start a brand new video on ionic bonding and upload that separately so that you can look at the two of them individually. So look through covalent bonding, make sure it makes sense to you. And if it does, move on to ionic bonding in the next video.